Hey, welcome to another episode of Earth is Our Home with Dr. Thomas Blaine. Today we're going to be looking at Part 3, History of Earth Climate. So stay tuned. Hey, welcome back to another episode of Earth is Our Home with Dr. Thomas Blaine. Today we're going to be looking at Part 3, the History of Earth Climate. Tom, I've really enjoyed our series because it's really enlightening. And you have some new information that I'm looking forward to hearing.
Well, that's fantastic. I enjoy doing this. I think a lot of people are very curious about the history of Earth's climate, you know, what's happened to Earth down through the millions of years that we've covered. We've covered the ages of the dinosaurs, the ice ages, and everything. We've talked about the reasons those have come and gone. And now on Part 3, we're going to come right up to the present, right up to spring of 2021 with temperatures. And I think a lot of people really do enjoy learning about Earth's climate engine and what makes it run.
Well, I think also it helps us to understand some of the myths, some of the beliefs that we have carried that may not necessarily be true.
That's absolutely right. You know, a lot of people sometimes have this attitude that beliefs are important. To me, beliefs are not important. Knowledge is important. And I always have put knowledge over beliefs. So the things that I've been talking about are items that have been well documented by scholars, and they're really fascinating. And I think that, we're going to continue to have a good series here.
Well, let's look at your power slide.
So here we go with Part 3 on history of Earth's climate. This is within the overall series, Earth is Our Home, in which we cover a wide variety of environmental topics. Note we're now into May 2021. We began in April. And so this is essentially the third installment in history of Earth's climate. So just to summarize a little bit what we've addressed, Earth temperatures are driven by different natural phenomena over different periods of time. So when we talk about millions of years or tens of millions of years, Earth's temperatures are driven by the position of continents, continental drifts. Where are the continents located on the surface of planet Earth? We covered that extensively in Part 1. When we get to thousands or tens of thousands of years, Earth's temperatures are driven by changes in Earth's orbit around the sun, Milankovitch Cycle, Milankovitch cycles. These are changes in Earth's orbit that occur somewhat regularly over periods of about 100,000 years. Think ice ages. What caused the ice ages to come on? Why did we get out of the ice ages when northern Ohio was covered with glaciers? How did that happen? It happened because of changes in Earth's orbit. We discussed that quite a bit. Now, when we get closer to decades or hundreds of years, Earth's temperatures are altered by changes in ocean currents and solar output. That is until humans came along fairly recently. So we're going to talk a little bit about those. We're going to bring it up closer to the present today. And, so this is the graph that shows Earth's temperatures since the end of the last ice age. As you can see, Earth was about a little over 4 degrees Celsius. That's about 8 or so degrees Fahrenheit cooler than it is today. We had a warming that was caused by Milankovitch, the changes in Earth's orbit. We had some upheavals occur along the way that almost sent us back into an ice age. But you notice those upheavals only drove Earth's temperature down about 2 or 3 degrees, which is about 5 degrees Fahrenheit. And then the Milankovitch forcing pushed us back up. We came into the maximum of this post-Ice Age period that we call the Holocene about 6,000 years ago. Since then, we've had some fluctuations. The Roman era warm period, the medieval warm period, the Little Ice Age. And so now we're going to look at actual temperature reconstructions. We are still reviewing. We did this last time, and I just wanted to pick up with that. Each color is a study that shows temperatures over the last 2,000 years. These are proxy temperatures taken from tree rings, ice cores, all kinds of things like that. If you look throughout, you'll see there have been some fluctuations. But if you look on the right, you'll see in the black line, that's actual temperatures taken by a thermometer. Those are global average temperature measured, not by proxies, but by actual thermometers. And as you can see, the signature of that looks different. Notice the warming trend in that one looks quite a lot different than the warming trends that happen naturally. And look at 2016, where we were when we had a strong El Nino that drove temperatures way up. So
I would assume that when you look at the average temperatures, it's just not going to one place. It's going to many places, to actually get that temperature.
yes,
Is that correct?
Okay, so these studies, for example, each one of these studies have temperatures, proxy data, for example. The proxy data is from all continents. In other words, we have sediments from all continents. We have ice cores from Antarctica and Greenland. All those things contribute to these studies. That's true. And then the black line on the right, we have weather stations all over the world on land and sea. So yes.
Okay, so it's just not one place; it's many.
No, we're doing global warming, global climate change. So this is all global. So now, when we get in and get away from proxy temperatures, we're talking about two ways to measure temperatures. One is surface-based. That's thermometers on the surface, on land and sea. We have data on that from the 19th century to the present. And then satellite data. We have satellites that are capable of measuring the temperature of the entire lower troposphere. That's from the surface of planet Earth up to 30,000 feet. That's a great way to measure, because you talked about different places. The satellite data is every place. Every place. And that's better, because if you've got a finite number of places, you could always ask, well, what's the temperature doing at places in between those weather stations? Well, there is no in-between weather stations on the satellite data, because it measures the entire lower troposphere. That's what we're going to talk about today. So here's the surface temperature data, and we got started around 1880. There were some data collected prior to that. We're going to start here around 1880. The black dots are annual averages. Again, these are for hundreds of weather stations all over the world. And of course, Antarctica, we began to do surface temperature in Antarctica in 1957. Different places have come on since then, but they've all been integrated to make this overall graph. If you look at the red line, it's a 5-year moving average. It smooths out the kind of drastic changes that you get. I mean, if you notice from 1900 down to about 1905 or so, there was a pretty major cooling that occurred there just over a few years. That's not typical. There are a lot of things that can cause that. Then another one occurred like that from about 1915 or so to 1917. We see there were some pretty radical warmings from about 1905 or so up to 1908, 1907, something like that. But we smooth those out with the red line. In any case, you'll see that global average temperatures rose in the early part of the 20th century. And then a cooling came in, very slight cooling between the 40s and the 70s. And I think we had talked before, by the 70s, because of that cooling trend, there were people saying a new ice age is coming. So a lot of people throw that up at me and say, well, you can't say any of this stuff, because I remember when we were talking about, a new ice age coming in. Well, there were definitely some reasons for that cooling. And they included a lot of increase in sulfate aerosols associated with the Industrial Revolution. There was also the sun kind of peaked out in its output mid-century. Has been trending down ever since. And we can talk about that in just a few minutes. But there are going to be blips. Overall, though, you see, we've got here 140 years worth of data, and the trend is unmistakable. Okay, we are literally up at an all-time record high if you look at what's going on with this data set. Now, some people complain about this data set. Places on planet Earth, temperature stations, weather stations may be located in proximity to where there's some development occurring. That development creates an urban heat island. Where I live, when I'm in town, I measure the temperature in town. I drive out into the country, especially in the summer, out in the woods, out in the country, just a few miles away, it's 3 or 4 degrees cooler. It's called the urban heat island effect. As we've developed more lands, some of those lands have encroached on areas near weather stations. That's going to cause recorded temperatures to rise. However, scholars that do this kind of work for a living have reported, and they do report, that they try to remove the urban heat island effect from this data. How successful they are, I'm not knowledgeable enough about the algorithms they use to do that. If you are worried about the urban heat island effect, don't worry too much, because now we have satellite data. So we have satellites that have been operating since January of 1979. And those satellites measure the entire lower troposphere. That's from the surface of planet Earth all the way up to 30,000 feet. So at any given moment, those satellites are measuring the entire atmospheric temperature from the surface to 30,000 feet. No urban heat island effect here. We're talking about the entire globe, not weather stations, just the entire lower troposphere. Now, if you look, a couple of things jump out at you. One is that if you look to the left, you see most of the data is below the zero axis. If you look to the right, most of it is above. That's warming. Now, each blue circle is a month. This data set began in January of 79. If you look at the little circle way out there on the left, January of 79, global average temperature was nearly 0.5 of a degree Celsius cooler than the average. That's that little blue circle. Each one of those is a month. The most recent month is April. So just a few days ago. So I've got you updated. This is as updated as you're going to get. Several things I want to say about this. The red lines, again, the red curve is smoothing, and it's 13-month averages. So you take 13 months, you plot a point, and you keep doing that. That way it tends to smooth out some of the highs and lows. Look at the high that occurred in 1980. There was a high there, and then in 1982, there's a low. and another high and a low. The red lines don't go to those extremes because those are 13-month moving averages. And so they kind of rule out the individual bounces of individual months. And that's called smoothing. It helps a lot in reading a graph. But what we're doing, like we did before on the, what was that, 5-year moving average. I don't do this, by the way. This is the folks that do the monitoring of global temperatures. They use a 13-month moving average. How they settled on that, what you don't want to have too long because it's not going to move enough. You don't want to have too short. So these are 13-month moving averages, and you can see all they do. Notice, pick a year. We had a massive warming in 1998, 1997, 1998. Look how high that went. And notice that the red line doesn't go that high because it's being pulled down by the fact that was 1 month way up the top. The other ones were a little bit lower and there are other ones lower still. So it still shows the same kind of trend, the warming, but it's not as extreme because the average for the period, you could have daily data on here. You just wouldn't be able to read it. You notice that there is a trend going up. In other words, essentially at the red line where we are now, we're about 0.3 of a degree Celsius. That's about 0.5 degree Fahrenheit above the average. Whereas before, back in the late 70s, early 80s, we were running at about 0.4 of a degree Celsius. That's 0.7 below the average. And you can see a lot of those like that. So if you go 0.7 and 0.5, that's about 1.2 degrees Fahrenheit that we've warmed in just 40 years. 1.2 degrees Fahrenheit we've warmed in 40 years. And remember what we were talking about. The difference between our climate now and the ice age is only 9 degrees. So we've gone up 1.2. So that's not trivial. That's about 15% of the difference to the ice age, only in the other direction. What causes these waves up and down, up and down? What causes that? You can't help but notice those. And those are caused by cycles of El Nino. Everybody's heard of El Nino, but nobody knows what it is. I'm going to teach you. First of all, La Nina. Imagine there's a high pressure system. You watch the weather every night. They show you where the high pressure is. They show you where the low pressure is. When a high pressure system develops off the coast of the west coast of South America, the high pressure, it's going to push winds away. If it's high pressure, it's wanting to get out. So it pushes. So there we go with the La Nina, where that high pressure pushes cold equatorial water away from South America all the way out toward the Philippines. The entire equatorial Pacific during a strong La Nina gets cold. Now, why is that water cold? That water's cold because it's coming up off Antarctica. If you look in the southern hemisphere, oceanic currents always go counterclockwise in the southern hemisphere. So imagine a big giant circle in the southern Pacific, bringing cold water from Antarctica off the coast of Chile, Ecuador. Now the wind blows it all the way toward the Philippines. Cold water. That cools down the ocean. The ocean mixes with the air in the atmosphere. That cold air spreads across the planet and cools the whole planet. Now, when the high pressure sets up near the Philippines, out in the Western Pacific, high pressure dome has moved. That's called the Southern Oscillation. The Southern Oscillation is the movement of high pressure systems. If you look on the weather map, one day we might have a high pressure system over Kansas. A few days later, it's over Florida. And then it's over the Gulf of Mexico. High pressure, low pressure moves around. When we're talking about high pressure in the equatorial Pacific, we're talking about the Southern Oscillation. If the high pressure dome sets up in the Western Pacific, it pushes wind away. It drives that water. It piles up water, moving easterly all the way to the coast of South America and even off the coast of California. If you look there, there's a red spot off Baja, California. That wind pushes warm water. As the warm water influences the air temperature, global temperatures rise. And this is what's driving these ups and downs. As you can see, if I put you to the test, guess what started just a few months ago? A very strong La Nina. In other words, the reasons we're cooling now over these past few months, and we've cooled a lot. Look at that. For the first time in quite a long time, we haven't spent very much time in recent years at temperatures this low. Why not? Because of global warming, because of what humans are doing to the environment. But still, La Nina is strong. And La Nina is capable, at least for a few months, of overriding that and putting global average temperature down to normal or slightly below. We were in a very strong El Nino back in 2020, if you look about a year or two ago. And remember, I showed you the 2016? 2016, we were at a very strong El Nino. That was the record high temperature recorded in the satellite era back in 2016. A very strong El Nino like that came about in 2016. One came about in 2019, went into 2020. But right now, our configuration is like that. And so that's what is doing these ups and downs. And those will always continue because the Southern Oscillation, where that high pressure system sets up, will always bounce around. But against that, we've got a warming trend. And you ask about solar activity, right there's what's causing the overall global warming trend. Carbon dioxide. You know, before humans came along in the Industrial Revolution, it was 280 parts per million. You look at that 320, it was 280 parts per million. By 1960, it had gone up to 320. We've got really good measurements since then. And now we're closing in on 420 parts per million of CO2, much greater amount of CO2. And CO2 traps heat in the atmosphere. The sun plays a role, but if you look at that the red, that's temperature since 1880. We already went over that in the one graph, the temperatures. But look at the yellow one. That's solar output. And as you can see, in the early 20th century, solar output was going up. Probably contributed a lot to that warming we saw on the graph. But since mid-20th century, solar output has been trending down. Notice the 11-year sunspot cycles. Each peak is about 11 years. Each valley is about 11 years. That's the solar cycle. But each cycle has been getting weaker in general as we've gone into the 21st century. We're at a period now of relatively low solar activity. And if we weren't, chances are the global warming we're experiencing would be quite a bit more than what it is now on either one of these graphs.
We're talking with Dr. Thomas Blaine, is an associate professor with The Ohio State University. Tom, it's always a pleasure listening to you and better understanding what global climate change is all about.